So what we're going to do today is basically put everything together into one curve sketching menu. So we get a function and we want to draw it. So things to look out for. Discontinuities. You remember we saw that before when it was back in term 1 we were looking at those sort of graphs, wasn't it? So bottom of the fraction can't equal 0, that sort of idea. We know that'll create a vertical asymptote. And when we did the polynomial division, the term by itself in front of the fraction turns out to be also an asymptote. Now y equals x in this case would be an oblique one, it'd be at an angle, but it might be a constant number and it's a horizontal asymptote. So those sorts of ideas still obviously come in handy with curve sketching. But now we can add to it some other things. So on our curve y equals function x, we know first of all we want to find stationary points. They're going to be some key points. So we'll find those, but now we can also classify them. So once we've found them, we can classify them as maximum turning points if the second derivative is less than 0, minimum turning points if it's greater than 0. Then we can look for points of inflection. So that's if second derivative is equal to 0, possibly we've got one. So again, we find our possibilities and then we go and classify them. So there's got to be a change in concavity. We could check either side or we could use our third derivative. Now, in reality, when you're drawing a sketch, you normally don't worry about finding points of inflection. Because you know, if it's a continuous curve and you've got a maximum turning point and a minimum turning point, well, somewhere in between it's going to have to inflect. I mean, it just has to. So, to be honest, the only time I find points of inflection is if they actually ask for it. And they might do that because they want to see, oh, do you know how to find them? But if it just says, sketch this curve, show important features, I'm not really that fussed about inflection points. I mean, turning points are important because you want to know how out or how far down it goes. X-intercepts, Y-intercepts, they're important. But points of inflection, not that important really. Okay, then if we're further investigating, we still haven't got an idea about the shape. We know the curve will be going up or increasing when the first derivative is positive. And it'll be going down if it's negative. And then concavity, we know it's concave up if its second derivative is positive, and concave down if the second derivative is negative. So let's do an example. It's just a polynomial, it's a cubic. So x cubed minus 6x squared plus 9x. First thing to work out is all the tools we're going to use. So first derivative, second derivative, and what the heck for this, I'll find inflection points for the sake of the example. So let's find the third derivative as well. Remember, explain what you're doing. So, okay, first step. I know stationary points occur when the first derivative is equal to 0, and this is why I'm now solving this particular equation. Actually, nicely 3 goes into everything, doesn't it? So I can do that. It gives me a simple little quadratic, x minus 1, x minus 3. All right, x equals 1 or x equals 3. Let's go classify them. So at x equals 1, the second derivative is negative. So I know 1 minus 1, make sure you substitute back into the y value to get the y value, strangely enough, is a maximum turning point. X equals 3, we get a positive try that again. X equals 3, we get a positive concavity, so we know that's a minimum turning point. And so, all right, let's find the point of inflection. We know that possibly will happen when the second derivative is equal to 0. In this case, 6x minus 12 equals 0, x equals 2. Now, logically, it must be an inflection point, because again, we've got a cubic. There must exist an inflection point. We've only found one possibility, so that's got to be it. Kind of not good enough for a proof. So, all right, we'll sub it into our third derivative. Oh, that was a constant 6. So it doesn't equal 0, so there is a change in concavity at that point. And, that actually was bad. Remember I said what I should have written down first was, therefore there's a change in concavity. So yes, 2 minus 3 is a point of inflection. All right, let's sketch it. There's 1 minus 1, 3 minus 5, and there's the point of inflection. Now, it's not a straight line, although those points would make us think, oh, look, lovely straight line. So let's find other things. Y-intercepts minus 5. X-intercept, I'm only going to bother finding X-intercepts if they're easy to find. cubics aren't necessarily easy to solve. I mean, we could play with random numbers and use our factor theorem and things like that, but otherwise I'm not going to bother. So in this case, when I draw it, and remember, we're not playing dot to dot, we don't get a zigzag, we have a curve. And notice how I creatively got away with finding the x-intercept there. I just said, oh, it'll keep going. It'll cut somewhere. But there's my curve, okay? All right, so that's what we'll look at today, a bit of curve sketching.